All right. Couple things. I noticed that Varn has assigned a homework assignment. So for those of you in Varn's class, you should start working on it. It mostly covers domain stuff and partial derivatives and limits, and talks a little bit about continuity, which we'll address right now with this example. So let's go ahead and do this one. And so I didn't really talk about this when we were talking about limits, but one way of kind of trying a bunch of paths at once is to let y, instead of letting like y equal x or y equal 2x or y equal 3x, you can let y equal mx. And then that's going to essentially say, well, for any line that goes to the origin, this is the limit value. And if it's not always the same, that's immediately going to show that it's not existing then. Let's see what happens when we do this. So let me do this one thing first. You can't pin your picture until someone else comes in. So, all right, there we go. So if I want to find this limit by letting y equal mx, so we're going to have the limit as x approaches 0 of 6x times mx squared over 2x cubed plus mx cubed. Now we're going to simplify. So that's going to be the limit as x approaches 0. Let's see, I'm going to have an m squared times 6. So I have a 6m squared. I have an x times x squared, so that's going to be an x cubed divided by 2x cubed plus m cubed x cubed. Notably, both the numerator and denominator have x to the third power in all the terms, so we can factor that out. So we could rewrite this as the limit as x approaches 0 of x cubed times 6m squared over x cubed times 2 plus m cubed. The x cubeds cancel or divide to 1, and we get the limit as x approaches 0 of 6m squared divided by 2 plus m cubed. There aren't any x's anymore, so as far as x is concerned, this expression is a constant, and the limit of a constant is that constant. So our limit is 6m squared divided by 2 plus m cubed. What does that mean for us? Well, it means that the limit doesn't exist, because if you pick different values of m, for example, if we pick, say, y equal to 2x, we're essentially saying m is 2, that's going to give us that the limit is 6 times 2 squared over 2 plus 2 cubed, which I don't know what that is. 6 times 4, 24, divided by 2 plus 8, which is 10, so 2.4. On the other hand, if we had y equal to just 1x, we'd be letting m equal 1, and our limit would be 6 times 1 squared over 2 plus 1 cubed, or essentially 6 divided by 3, which is 2. Those aren't the same. And we already knew they weren't the same based on the fact that our limit has m's in it, right? If our limit, or if our limit is dependent on the value of m, and m can be any real number, then this is going to have different values for different inputs of m. So if you take a limit like this and you get something that has m in it still, that's almost always going to mean that the limit doesn't exist, because you're getting different values along different paths. Sometimes you'll do something like this and you actually will get the m's to go away. Like you get something like 0 probably. And then you have to try something else or start going down the path of maybe this limit exists. Oh, sorry, I can't see the bottom there. I apologize. The other thing I'll mention here. So let's talk about continuity for the briefest of moments. Maybe. So if we look at this function, the function that I just wrote the limit of. So if I said my function was f of x comma y equal to 6xy squared divided by 2x cubed plus y cubed. We know that this function couldn't be continuous at 0, 0 at the origin because it's not defined there, right? This is not even defined at 0, 0. And to be continuous somewhere, the function has to be defined there, right? That's one of the requirements. So let's fix it. Let's make a new function that's almost the same. Let's say g of x comma y is equal to the piecewise function 6xy squared over 2x cubed plus y cubed when x comma y is not 0 comma 0 and it's equal to 0 when x comma y is 0 comma 0. So let's ask a couple questions here. So find a place to put my papers where I don't. So part one, is g of 0, 0 defined? Well, yes, we just defined it, right? G of 0, 0 is 0. But as we just saw, is the limit as x, y approaches 0, 0 of g of xy defined? And the answer is no, right? We just took that limit and saw, oh yeah, the limit doesn't exist. No, that limit as xy approaches 0, 0 of our g of xy does not exist. So even though this function is defined at the origin, the limit doesn't exist there. So we still don't have continuity. So I'll point out that f of xy, sorry, g of xy, apologies. G of xy is not continuous at 0, 0 because the limit as xy approaches 0, 0 of g of xy doesn't exist and therefore couldn't be equal to g of 0 comma 0. It's just like with regular functions of one variable back in the day when we said, oh yeah, the function is continuous if the limit exists and is equal to the function value, the same thing is true for functions of two variables. The function is continuous at a particular xy coordinate if the function exists, the limit exists, and they're equal to each other. So an easy example, which I don't think we'll go through it real quick here just because I think it is somewhat worthwhile. So here's an example that's going to feel maybe too easy. Oh well. Let's say our f of xy is equal to, I don't know, log base 2 of x cubed plus y squared. And the question we're going to ask is f of xy continuous at the point 2 comma 4? So we're going to do three things. They're going to feel not that challenging. So thing one, does it exist there? So what is f of 2 comma 4? Well, we can plug in the 2 and the 4 and get log base 2 of 2 cubed plus 4 squared, which is log base 2 of 8 plus 16, which is 24. And unfortunately, there's not really anything else we can do with that. That's fine. It's a little number, right? It's real. Question 2, does the limit exist? So we're going to take the limit as xy approaches 2 comma 4 of log base 2 of x cubed plus y squared. But then we're just going to plug in 2 and 4 for x and y and get the same exact result. And the third question, are they equal? Obviously, yes. So that means the function is continuous at that point. So we can conclude that this function, f of xy equal to log base 2 of x cubed plus y squared, is continuous at that point. Other points, maybe not. Certainly wouldn't be continuous at, say, like -1 comma 0, because it wouldn't even be defined there. But that's a really kind of straightforward example of how we could see a function is continuous at a particular xy input. Before I forget to do this. Here's the attendance form. If I do forget the attendance form, like it gets like halfway through class and I haven't passed it, remind me. I usually try not to forget, but sometimes I get distracted by the math. For those of you on Zoom, let me share with you. virtual attendance form. There we go. Cool. So, questions about any of the things we've done so far? We don't spend a lot of time concerning ourselves with continuity in this class, but we do talk about it briefly. All right, well, let's go ahead and look at, and then we talked about partial derivatives last class. Partial derivatives are going to be with us for the rest of the course, pretty much. Maybe not for like the last couple of weeks, but essentially from now on, partial derivatives are going to be something that's just always there as part of almost anything we do. Yeah, I think so. I think so, anyway. That sounds about right. So the next thing we're going to talk about are tangent planes. Tangent planes, not lines, and linearizations. But before we do that, let's actually go back and talk about how we found tangent lines in linearizations. So recall from your 17A days, we can find the equation of the tangent line to y equals f of x at some point x naught comma y naught is given by, I always think of it this way, y minus y naught equal to f prime of x naught times x minus x naught. Or y minus the y coordinate equals your slope times x minus the x. Oh, let me see if I can fix that. But thank you. And then the linearization is practically the same thing. So the equation of the tangent line is this. The linearization, again, of f of x at the point x naught comma y naught, we're literally just going to isolate y and call it L of x. So we're going to say that L of x is equal to y naught plus f prime of x naught times x minus x naught. Or written slightly differently, L of x is f of x naught plus f prime of x naught times x minus x naught. Again, really just the equation of a tangent line. Here's what we used it for back then. So someone could have asked you, for example, to say, find the linearization of, let's change it up, sure. F of x equal to the cube root of x, and use it to approximate or estimate the cube root of 29. Sure, I'll probably work out to be okay. So here's the idea. I'm going to draw the graph of this, although I'm going to draw it really, really not at all to scale. My cube root graph looks, I don't know, kind of like, I do know, I shouldn't say I don't know. I definitely know what the cube root graph looks like. It looks kind of like this. This kind of deal. So I didn't, or I should say, I left out an important piece of information. Where are we doing the linearization? Well, we want to pick a nice value to plug into the function that's close to the value that we're trying to approximate at. So what's a number that's close to 29 that's easy to take the cube root of? Right, 27. So I would say that our x naught value here is 27. And our y naught value is the cube root of 27, which is 3. The idea is that over here, and again, my graph is not to scale. That's okay. Over here at 27 comma 3, we are finding the equation of the tangent line. So this tangent line is our linearization. And again, not too terribly, our linearization is just going to be our f of 27 plus f prime of 27. We have to find that times x minus x naught, which is still 27. Okay. So then if I have to find the, so I know that this is going to be 3 plus, but then I have to figure out what f prime of 27 is. So let's see, my function is the cube root of x, or x to the 1/3. My f prime of x is going to be 1/3 x to the negative 2/3, which I would rather write as 1/3 times x to the positive 2/3. This makes it easier to plug something in a minute. So then, if I plug in my nice value to input, which is 27, f prime of 27 is going to be 1/3 times 27 to the 2/3 power. 27 to the 1/3, or the cube root of 27 is 3. 3 squared is 9. 9 times 3 is 27. I didn't really want to get 27 again, but oh well, that's life. So that's my slope. So at this point, the slope of that tangent line is 1/27th. Or you go over 27 and up 1. So here's our linearization. It's 3. I was going to write it there. Oh well, I didn't. 3 plus 1/27 times x minus 27. And I would say most of the time, it's not advantageous to simplify this any further. This one is probably an exception because the 1/27 and the 27 would multiply nicely to just 1. But generally, it is not going to be helpful to simplify this further. Because then what we're going to do is we say, well, cool, this linearization is an approximation of this function near this point. If you move further away from that point, the approximation gets less good. But if I wanted to, say, approximate the cube root of 29, I would say it's approximately equal to the linearization with 29 plugged in. Check it out. If we plug in, I'll go over here. If we say like 29 is right there, if I plug in 29, here's the function value, which we're actually not going to get. And then a little bit higher up, there's the value that we're actually going to calculate. So over here, that is our L of 29, which is a good estimate of the function evaluated at 29. So let's see, if we plug that in, we're going to get 3 plus 1/27 times 29 minus 27, which is 3 plus 2/27. And you can get a common denominator, I guess, or you could leave it like this. I would probably leave it like this. I think this is kind of more useful. But if you actually get a common denominator, it's going to be 81 plus 2, so 83/27. I don't feel like that's any better. Just to satisfy our curiosity, my curiosity really, how good an estimate is this? Well, if we actually take the cube root of 29, 29 to the 1/3 power is going to be about 3.07. Whereas if we look at 83 divided by 27, we get 3.074. So, right, pretty close. Thanks, appreciate it. 3.072 versus 3.074. Our answer was a good estimate of the actual cube root of 29. Neat. So now the idea is we're going to extend this. We're going to say, instead of doing a approximation of a line, we're going to do approximation of a plane. Essentially, we're just going to add another component. All right, let's do it. So really, I'm just going to take these things I wrote here, and the thing I'm about to write is going to look almost the same, just with like another part added on, because we've got another dimension. So in 3 dimensions, we have to modify these equations. So instead of a tangent line, we have the tangent plane to a surface. The idea here being that if you have some, I'm really not great at drawing this, but I'll try my best here. If you had some surface, like I'm kind of imagining the thing I'm about to draw is like part of a sphere in the first octant. Like you've got this part of the sphere there, and I want to say, if I go over here, over that way, that way, that way, like right here, if I wanted to try and find like the tangent plane, it would look kind of like that. Just drawing a little bit of it to not kind of ruin the picture, right? But we've got this plane that's essentially sitting just on one point of the surface. And then as you move, if you look close to that point, the approximation is going to be good. If you move further away from that point, the approximation is going to be less good. So here's what we get. The tangent plane to the surface f of x comma y at the point x naught comma y naught comma z naught. I might even call this z equals f of x y, but okay, is the following. So just like before, instead of it being y minus y naught equal to the slope times x minus x naught, it's going to be z minus z naught equal to the slope in the x direction times x minus x naught plus the slope in the y direction times y minus y naught. So really and truly, almost the same equation that we just looked at. I'm just kind of adding on another piece. And then in a similar way, the linearization, it's virtually the same thing. The linearization of f of x comma y at the same point, x naught comma y naught. Again, we're just isolating z and then replacing z with L of x comma y. So we're going to rewrite it as L of x comma y equal to, I think I'm going to call z naught, but I'm going to write as f of x naught comma y naught. That is just your z naught. And then we have this part still, plus partial derivative with respect to x, evaluated at the point x naught comma y naught, times x minus x naught, plus the partial derivative with respect to y, evaluated at x naught comma y naught, times y minus y naught. So pretty much the same thing we just saw, we're just adding another dimension. Cool. So let's look at an example. So example, we want to, let's see, find the linearization of the function f of x comma y equal to x cubed times y to the fourth at the point 2 comma 1, and then use it to approximate the value of f of 2.2 comma 0.9. All right, so if I'm finding a linearization, whether it's one variable or two variables, I need to find the derivatives. Really, that's something I always need. So here I need the partials. So my partial derivative with respect to x is going to be 3x squared times y to the fourth. My partial derivative with respect to y is going to be x cubed times 4y cubed. And I also really actually need to plug in the convenient point they've given me here, right? So unlike last time, they gave me a nice one here. If the question had been phrased like find a linearization of this function and didn't tell you the point, and they said and then use it to approximate f of 2.2 comma 0.9, this here I think is a pretty big hint that the point we should be using is 2 comma 1. Easy values to plug in that are close to the values we're trying to approximate it at. So if they don't tell you the point, look at the thing you're trying to estimate and go, well, what's close to that that's relatively straightforward to just put into the function. So then our partial derivative of x evaluated at 2 comma 1 is going to be 3 times 2 squared times 1 to the fourth, which is 12. And our partial derivative with respect to y evaluated at 2 comma 1 is 2 cubed times 4. I don't really need to write times 1 cubed, but I am. 8 times 4 is 32. So then we're going to write the linear. Oh, and I guess I need to, you know what else I need? I need f of 2 comma 1, right? I need my z naught is f of x naught, y naught, which is f of 2, 1, which is going to be 2 cubed times 1 to the fourth, which is 8. All right, now we have, I think, all the pieces we need. In fact, just looking at my linearization up there, I'm just going to copy this down and plug in all the things. So my linearization at x comma y is equal to my z naught, which is 8, plus my partial with respect to x evaluated, which is 12, times x minus the x coordinate, 2, plus my partial with respect to y, which is 32, times y minus the y value, which is 1. And I'll point out here, it's really not helpful to simplify this if we're trying to plug in the next point. If we look, how do we simplify? So I simplify this, I get 8 plus 12x minus 24 plus 32y minus 32, which I can simplify. Let's see, 8 minus 24 is negative 16, minus 32 is negative 48. I can write this as 12x plus 32y minus 48. And then when I plug in 2.2 for x, 12 times 2.2 isn't like that hard, but it's more work than I really need to be doing. It's much easier to plug in 2.2 here, subtract 2, and then 12 times 0.2, I think is an easier thing to calculate. So usually you don't want to simplify this. You want to leave it as is. I would say the only reason you might want to simplify this is if they ask you for the equation of the tangent plane as opposed to the linearization, then writing this with z instead of that, or even rewriting it so you had something like 12x plus 32y minus z equal to positive 48. That's probably the more like normal-ish way of writing the equation of a plane. But it still wouldn't be wrong to write it this way if you replace that with z. Anyway, back to the question. If we're trying to approximate f of 2.2 comma 0.9, we're going to say that f of 2.2 comma 0.9 is approximately the linearization evaluated at that point, 2.2 comma 0.9. And then we're going to get, let's see, 8 plus 12 times 2.2 minus 2 plus 32 times 0.9 minus 1. That's going to be 8 plus 12 times 0.2 plus 32 times negative 0.1. That's going to be 8 plus, let's see, 12 times 2 is 24, so that's going to be 2.4. And 32 times 0.1 should be 3.2, so it's minus 3.2. So I have 8 plus 2.4 minus 3.2 is going to be 8 minus 1.2. Yes, which is 6.8, unless I've made a mistake. I think I have made a mistake. Nope. Yeah, no, Grant made a mistake in his notes here. That's the problem. Yeah, I should correct that. It's a mistake. I feel like I'm doing something crazy here. Nope, I'm making a dumb error that I'm just not seeing. Yeah, I totally am. Sorry, I apologize. This is a mistake right here. 2.4 minus 3.2. What is that? It's not 1.2. It's I think it's actually 0.8, negative 0.8. So sorry about that. Apologies there. This should be 10.4 minus 3.2, which is going to be 7.2. There we go. Sorry. Small error there. I mean, subtracting some decimals. That's why I was trying not to let you see it before. Yes, you would. It's a little bit more work to do it that way, depending on your perspective. And sometimes things are uglier than this, and so it really is a lot more work to do it if you simplify it first. But yeah, if you were to do, if you were to use this instead, you should still get the same answer. But 12 times 2.2 plus 32 times 0, especially the 32 times 0.9, that doesn't seem like fun. But it should equal 7.2. It's just more work to do it that way. I always like to check to see how close was I. So we actually plugged in, f of 2.2 comma 0.9, which would be 2.2 cubed times 0.9 to the fourth. Not that it wouldn't be impossible to do this by hand. It would just be tedious, right? 2.2 to the third is doable, but not fun. Same for 0.9 to the fourth. So 2.2 to the third times, don't do that, James, times 0.9 to the fourth gives us a value of 6.986 approximately. So not too bad. we're not too far away from 7.2, or we're not too far away from the right answer with our estimate of 7.2. Sure, let's do one more. Well, one more that is just kind of straightforward, and then we'll talk about a couple other things. We got time. I'm trying to convince myself we have time. So, similar question, but slightly different. Here we're trying to find the equation of the tangent plane to the function f of x comma y equal to 4x squared minus y squared plus 2y at the point -1, 2, 4. I would like you all to try this one on your own. So I'll remind you, you need to find a few things. You need to find the partial with respect to y, evaluated at -1, 2. I should have done x first, maybe. That's more normal. The partial with respect to x, also evaluated at -1, 2. So find the partials first, then plug in the point. Those will be your slopes, and then your equation of your tangent plane should look something like z minus your z coordinate equal to your partial with respect to x evaluated at -1, 2 times x minus your x coordinate plus your partial with respect to y evaluated at -1, 2 times y minus your y coordinate. And you should know that your x coordinate is -1, your y coordinate is +2, and your z coordinate is +4. So give that a try. Find those partials, plug in the point, and then throw it all into this formula here. Maybe like 2 minutes. Seems like it's long enough. That other paper go. Okay. We'll work on that problem. Oh, yeah. Yes, let me circulate the dependency. Oops. Background, which you didn't get it. How did I miss him? No. Sometimes things happen. I know it's hard when only one of you is here because I'm just guessing, like, this is one of you. I'm not sure which one because the name's the same. All right, that's been 2 minutes. So let's go and find these partial derivatives. So our partial with respect to x is going to be 8x. And then if I plug in the point -1, 2, I'm going to get 8 times -1, which is -8. The partial with respect to y is -2y plus 2. If I plug in the point -1, 2, I'm going to get -2 times 2 plus 2, which is -4 plus 2, which is -2. Those are my slopes. So then my equation is going to be z minus the z coordinate, which is 4, equal to the partial with respect to x, which we just said was -8, times x minus the x coordinate, plus the partial with respect to y, which was -2, times y minus the y coordinate. I'd probably simplify this. So if we simplify this just a little bit, we get z minus 4 equal to negative 8x. Negative 8 times positive 1 is also minus 8. And then minus 2y plus 4. And if I was writing this in the standard way, I'd probably bring everything to the left and say I have 8x plus 2y plus z equals, I usually put the constant on the other side, so negative 8 plus 4 plus another 4 is going to be 0. So that's probably how I'd write the equation of the tangent plane as opposed to the linearization. And you can kind of go either way. I personally like to write it this way because it feels more natural to me, but some people prefer to isolate z. So you can write it like this. Another perfectly good way would be write it as z equal to negative 8x minus 2y. Oh, don't cut off the 0 there. Sorry about that. Not a 10. That's a 0 with an accidental line in front of it, which I will white out before I post these notes. Yeah. Well, so I didn't get rid of the 4. They happen to add to 0. So what's happening here is from here, right? If I bring all the x, y's, and z's to the left, I get 8x plus 2y plus z. And on the right-hand side, I have negative 8 plus 4. And then if I add over this other 4, yeah, add up to 0. That's awesome. Yeah. I don't care. I'm not the one grading your work, right? I'll point this out, right? I am not the person teaching the actual class. So as far as you're concerned, you should do it however your instructor wants you to do it. Either way is probably fine. Yeah. All right, let's see. How much time do we have? Okay. So let's look at one more example that's more of a word question than like a just throwing stuff at you, but it's still kind of the same. So yeah. So here's what we've got. This is section 9.3, number 22. Just so you have a reference point. So the problem goes something like this. A model for the surface area of a human. I wonder how people came up with this. I'm curious, like where this function came from. A human body is given by the following. S is equal to a function of weight and height is equal to 0.1091 times your weight in pounds raised to the 0.425 power times your height in inches to the 0.725 power. So weight is in pounds, height is in inches, and the surface area is in square feet. So definitely there's no use in trying to there's no dimensional analysis here where you plug in, you're just like, oh, well, these units multiply. No, it doesn't make any sense. Someone came with some weird formula based on pounds and inches, and then the output is being measured in the units of their choice, which was square feet. Kind of strange, whatever. So, let's go ahead and do the following. We want to first find the linearization of this function s equal to f of w comma h with a weight of 160 pounds and a height of 70 inches. All right. These are not particularly convenient values, but they're what we've been given. Because it's not like, I mean, there's no convenient values here. Anything raised to the 0.425 power is probably not going to be nice. All right, so here's what we've got. We've got that the partial in the W direction is 0.1091 times 0.425, which ends up being approximately 0.0464 times W to the 0.425 minus 1 is negative 0.575. H still sticks around as is. And then instead of writing parentheses with the points I'm going to plug in, we are going to write a vertical line to show that we're evaluating at, and we're evaluating at a weight of 160 and a height of 70. If you plug those in, you get approximately 0.0546. You could actually pull out the calculator and do it, right? It's going to be gross. 0.0464 times 160 to the negative 0.575 times 70 to the 0.725. Okay. Similarly, our partial derivative with respect to h is going to be approximately, well, now it's going to be our 0.1091 times 0.725, which is about 0.0791 times W hangs out as is. So W to the 0.425, right? It's just acting like a constant multiple. And then our H's power is going to be one less. H to the negative 0.275. Kind of terrible. Plugging in the same point, a weight of 160 pounds and a height of 70 inches. And we're getting approximately, where'd you go? 0.213. Yes, yes. So this first number here and here, this is our 0.1091 multiplied by 0.425. And this one is our 0.1091 multiplied by 0.725. Approximately. Here's what I'm seeing by it. So just to kind of think about what's happening here, I'm seeing the following. If I increase the weight, well, since the partial derivative with respect to the weight is positive, that means increasing the weight should increase the surface area. Specifically, if I increase the weight by, say, 1 pound, my surface area should increase by 0.0546 square feet. And if I increase the height by 1 inch, my surface area should increase by approximately 0.213 square feet. Kind of nice to think about what these partial derivatives kind of mean. They're saying, right, as one thing increases, the other thing increases this much. All right, so now we can probably fit this in here. Oh, I also need the function evaluated at the point. So f of 160 comma 70 is going to be approximately, well, it's going to be 0.1091 times 160 to the 0.425 times 70 to the 0.725, which if we plug this into a calculator, we get about 20.524. So here's what this is telling us. This is telling us that if someone weighed 160 pounds and was 70 inches tall, which is 5'10", we would estimate them to have about 20 square feet of surface area. Interesting. So now we'll write the linearization. Our linearization, again, this is really just throwing it all in the formula. The linearization of, I shouldn't be using X, I should be using W comma H. Let's just write that again because that looks terrible. The linearization of W comma H is going to be, well, it's our L of W naught H naught plus the F, goodness James, F of W naught comma H naught plus our partial with respect to W times W minus W naught plus our partial with respect to H times H minus H naught. And then we're just going to plug in the numbers. So our F of W H naught is 20.524 plus our FW, which was about 0.0546 times W minus the initial weight, which is 160, plus our FH, which is 0.213 times our H minus our H naught, which was 70 inches. Gross. Sometimes the numbers are gross, especially, I feel like especially in this class, the numbers are often not very nice. So here's what we're going to do with this. We have enough time? Yeah, we have 5 minutes. So part B here, we're now going to use the linearization we just found to approximate or estimate the surface area of a person weighing 162 pounds with a height of 73 inches. So something I'll point out here, the linearization is not any easier to calculate than the original function, right? So this is kind of a counterintuitive example, in my opinion. In the previous examples, we were plugging in nice values and getting out nice values. Here, it would be better, since we're already going to have to use calculators to do this anyways, to have plugged it in just to the original function. But the point of the question isn't to see that one way is easier than another, or not. It's to show you that if you do this versus if you do, sorry, there's also an and here, and we're also going to do it for a person weighing 170 pounds with a height of 80 inches. It's quite tall, 6'8". The point of this question is to see that the further away from the initial point that we chose we are, the more error there is in our estimate. So if we do the first one here, and I really feel like writing it all out is not super necessary, but the linearization at 162,73 is going to be, well, I'm just plugging it in here. It's going to be 20.524 plus 0.0546 times 162 minus 160, 2, plus 0.213 times 73 minus 70, or 3. And if you plug that all in, you get approximately 22.255 square feet. Contrast that with just the function itself evaluated at 162,73. We're going to get approximately, well, we're going to get actually, if I plug it into the function, it's going to be 0.1091 times 162 to the 0.425 times 73 to the 0.725, which ends up being approximately 21.271 square feet. So pretty close to each other, right? The estimate we got of 22.2 is pretty close to the actual value of 21.2. We're off by like 1 square foot. On the other hand, if we look at the other values we mentioned, the linearization when the weight's 170 and the height is 80, all right, I'm not going to write it all out. I can, by writing out, it doesn't show you anything, right? Let's just say what it is. It's approximately, I lied. I should write it out. Sorry. It's 20.524 plus 0.0546 times 170 minus 160 is 10 plus 0.213 times 80 minus 70 is also 10. And we get approximately how much? We get approximately 28.114. On the other hand, if we plug those values into the original function, we're much further away than we were in the previous example. We're going to get a value of 0.1091 times 170 to the 0.425 times 80 to the 0.725, which ends up being about 23.201 square feet. So here we're off by like 5 square feet, whereas here we're off by 1 square foot. And the reason we're off by so much more is because we've moved further away from the point of tangency. I'll show you this picture instead of trying to draw it. Here's a picture kind of showing this. The idea here is that, you see that? You can't see that. Let me go there. So like here's our point of tangency, and here's our tangent plane, and here's our surface. And the closer point, 162,73, has a difference that's not nearly as big as the difference when we plug in the 170,80, which is much, much larger because the tangent plane is further away from the surface the farther away you go from the point of tangency, typically. All right. It's almost 1 o'clock. I should stop.